Hi folks, welcome back to Physics with Captain Rod. The purpose of this video here is to demonstrate how to apply principles that I talked about in my previous videos about harmonic motion to a rotational type of system here. So what we're looking at, imagine we've got this 2-meter rope with this 5-kilogram object attached to it. This picture is meant to be a picture of the system at equilibrium. All right, imagine now that this system is displaced an amount I call theta max here and released. So for the rest of this problem here, I'm going to call this my picture 1 here. And what we're going to try to calculate is the frequency of oscillation of this system. So if it's released from rest here, picture 1, this system's going to oscillate back and forth between these two positions. It's going to do something like this. And what we're going to try to do here is get the frequency, just the angular frequency of the system. I'm sorry, not angular frequency, the frequency in hertz. Now, this is my second picture here, and I'm going to use these two pictures now to kind of analyze the problem. In picture 1 here, this theta that I'm calling theta m here, it's standing for theta max. It's important to realize this is a fixed numerical value in this problem. It is some number. This theta, however, is a function. This guy right here is time dependent. And in order to get the frequency, we're going to have to write equations here between these two pictures involving this theta here. Now, hopefully you've seen my videos on how to analyze these harmonic or oscillating types of systems. One way is by Newton's second law. Second way is by energy methods. I'm going to go ahead and use energy methods on this. So what I'm going to do is I'm going to write out a work energy equation between 1 and 2. PE1 plus KE1 plus work equals PE2 plus KE2. We'll start with this. Now, at position 1, the system starts from rest, so that term is going to be 0. Anytime you're dealing with potential energies, you have to define a datum. I like to use the rotation point, like the pivot point here. That's a good place to put a datum for systems like this. The problems just work out kind of nice. I'm going to choose this as my datum. That's going to make my PE1 term equal to minus mgl cosine theta max. Now here's where I'm getting that from. First of all, we're down below our datum. That's why the potential energy term is negative. The distance below our datum is this distance right here, which by this right triangle, that distance is adjacent to theta. Hypotenuse is basically equal to the length of the rope. You might argue there's a little tiny distance here. Whether we're talking about here to here or here to here, not super important for the problem. We'll assume this thing's pretty small compared to the length of the rope. So the vertical distance here would be L cosine theta max. Work term, also 0. Whoops. And the reason that work term is 0, if I think about the different forces acting on the system, there's a gravitational force here down, but I'm taking that into account with a potential energy. There's a tension acting kind of up and right, but that's internal to the system. I'm sorry, not up and right, up and left, but here it's acting kind of down and right. The tension, and even if it wasn't internal to the system, the tension doesn't do work anyway because the tension always is at a right angle to the motion. One could argue there's an external force here applied on the rope, but there's no displacement here for that point. That point's not moving, so there's no work done. So there's no reason to have a work term. Equals. All right, position 2. My potential energy term is going to be hinged on this distance right here. And again, from this triangle, that distance, that vertical distance, is adjacent to theta. Hypotenuse is what we're calling L. So the PE2 term is going to equal minus mgl cosine theta. Now the difference between these two terms, this one is a theta max. It is just some number. But this one is a variable. As you know, position 2 can be anywhere as it goes back and forth. All right, the KE2 term. Now, this object is almost big enough to consider it being kind of three-dimensional, and we almost need to treat this like a rotational problem. What I'm going to do is just say, all right, this object's pretty small. I'm going to treat this like a point mass moving this way with a speed v, and therefore the kinetic energy is equal to 1/2 mv squared. Now, I couldn't get away with that if this was a really large object. You know, if this were something like this, rotating about this point, we would have to calculate the moment of inertia of this object about this point, and we would have to do the rotational term that way. But as long as this thing is pretty small compared to the length, we can express the kinetic energy term as just 1/2 mv squared. Notice, however, though, that, in essence, I'm almost introducing another variable here, because we have v and we have thetas. Well, because of the rotational motion of this object can be considered to be rotating about this point, which means this translational v here is equal to L times the angular velocity of this object about this point. I'm going to just call that theta dot, again, where theta dot is the angular velocity, sometimes called omega. So the kinetic energy term can be expressed 1/2 m v, which can be written L d theta dt squared. The reason for doing that, now when I look at this equation, all I see are thetas. Now, this equation is set up in such a way like you tell me a theta, I'll tell you a theta dot, or you tell me a theta dot, I'll tell you a theta. But that's not what we want. What I want is frequency, and frequency is number of cycles per second. I can basically convert this equation to a time-dependent equation by time differentiating it. Both sides, everything. Left-hand side now. These are all fixed numerical constants, so the time derivative of this entire term is 0. This guy, now we got a lot of constants here. The derivative of cosine is minus sine, so that's going to be plus mgl sine theta. But this has to be chain ruled. Theta itself is changing, so the derivative of theta, theta dot. Write that theta a little more. Theta dot. There we go. Plus, now I'm going to look over here. All right, this 2 is going to come down and basically cancel that. So we're going to have ml squared, and it's L squared because L squared, theta dot to the first power, because this is theta dot squared. Theta dot also changing, so it's time derivative, theta double dot. All right, so here's my equation of motion for the system. Now you'll notice that these cancel. Standard form for differential equations, highest derivative first with a 1 in front of it, which means I need to divide out this ml squared. So what are we going to have here? We're going to have, we divide this by ml squared, we are going to have g over L sine theta. I think that's it. Equals 0. We'll take a look at that again. So we're dividing by ml squared. The m's are definitely going to go away. The g stays. L over L squared is 1 over L, and the sine theta stays. All right, so I got my equation of motion for the system now. So what I'm going to do is get rid of this stuff. You know what? Instead of getting rid of it, we will just shrink it for future reference. All right, now, next step here. What do we do with this guy? So this one we got to do some observations here. This one doesn't have the quite the same form as the one in my previous example. This equation is a nonlinear equation here. It does not have the form of something like y double prime plus a number times y equals 0. Equations of this form have trig solutions because you're looking for functions that you can differentiate twice, add to themselves, and get 0. This equation doesn't have that because of that sine theta part. But what we can do is we can imagine this theta max not being a very large theta. We're going to use what's called the small angle approximation. And for small angles, as long as theta is small, then sine theta is approximately equal to theta. If you've had a calculus class, everybody has looked at this limit. You know, limit as theta goes to 0 of sine theta over theta. That's a pretty common limit example to do in calculus. That limit is 1 because for small angles, these two things are equal. I think I'll save the physically wise for another video. So for now, I'm going to apply small angle approximation to this, which means I can write this theta double dot plus g over L times theta equals 0. This equation is good as long as we only apply it to cases where this theta max is small. All right, this now does have trig solutions. So the solution of this equation has to look like, maybe a C1 sine omega t plus a C2 cosine omega t. Now, if you have initial conditions, that will force the values of C1 and C2. Usually these problems, you'll end up with either the sine part or the cosine part, and the initial conditions will tell you which. If you only want the frequency, if all you want is the frequency, that means that you can just ignore the initial conditions, because this problem, this thing's going to oscillate back and forth. You can start t whenever you want. You do not necessarily have to start it with conditions given, if all you want is the frequency. The frequency is in this term, the angular frequency, or it's in the sine and cosine part of it. So what I'm going to do here is I'm just going to throw this term out. Actually, I guess technically, let's do this. Just to be at least somewhat consistent with my problem here, at t equals 0, theta is some value. This would be the appropriate one to throw out here. So I'm going to just keep the cosine part of this. So I'm going to get rid of this stuff. And to get the frequency, you need this guy. So I'm going to start with, whoops, oh, and I see a little mistake here. This is supposed to be just theta equals my solution, not theta double dot equals. So I'm going to start with theta equals C2 cosine omega t. Now, why did I throw this part away? I only need one of these to get the angular frequency, and it doesn't matter which. Theta dot is going to equal minus C2 omega sine omega t. Theta double dot is going to equal minus C2 omega squared cosine omega t, going through the time derivatives of these. And now what we're going to do is we are going to sub this and this into our differential equation and see what we got here. So theta double dot is this term, minus C2 omega squared cosine omega t, plus g over L times theta. Theta is given by this function, C2 cosine omega t, and then equals 0. Now this equation can be factored. I'm going to go ahead and do that. We can factor out the cosine part and the C2. So we're going to have C2 cosine omega t, and what we're left with is going to be minus omega squared plus g over L equals 0. And here's where we're going to get our frequency from this. So the omega, the angular frequency, is square root of g over L, which is going to equal the square root of 9.8 meter per second squared over, in this example, we're looking at 2 meters. And I'm going to go ahead and calculate a value. I get 2.21. I'm just going to approximate that to 2.2. So this is approximately 2.2 radian per second. So what that means is our solution is going to look something like this, some sort of C2 times the cosine of 2.2 t. Now, the value of C2 doesn't matter. We're not going to need that to get just the angular frequency. Suffice to say, it's some number. All right, so now when I graph this, what we're looking at is a cosine wave. I wish my program here had like a cosine wave generator. Theta against time. Standard cosine waves, this is going to look something like this. And again, a really important part of the graph is one complete cycle, which is here. That time is the period. And at that point on the graph, 2.2t has to equal 2 pi, because we have cycled through one complete wave here. That means this right here is 2 pi. And if I solve that for t, we get 2 pi over 2.2. I get approximately 2.85 seconds. I'm just going to round that again. I'll hold 3 on that one. All right, 2.85 seconds. Technically, I should probably carry more sig figs earlier in the problem, but this is good enough just for demonstrating. This is the period of oscillation for this system. It's going to take 2.85 seconds for this system to oscillate back and forth. And then the frequency of the system is 1 over the period, so that's going to be 1 over 2.85 seconds, which is right around 0.35 hertz. All right, so what have we done here? We were able to calculate the frequency in hertz of a harmonic system, or of a mechanically vibrating system. How do you do that? You start by writing the equation of motion for the system. You write out an energy equation, or at least this is one way, between two positions, and then you hit it with a time derivative. Out will come the equation of motion for the system. When there are sines and cosines, that makes the equation nonlinear. So what you have to do is you use what are called small angle approximations. If you see a sine theta, this will be approximately equal to theta for small thetas. And if you see a cosine theta, this will be approximately equal to 1 for small thetas. You have to get the equation into a form that looks like second derivative plus a number times y equals 0. So you can't have any sines or cosines in this term. Once you get the equation in this term, then you write out your general solution, which, if it's a rotational problem, if you're using theta to describe the position, it'll look something like this. Theta equals c1 sine omega t plus some maybe c2 cosine omega t. If all you want is the frequency, you are free to choose either one of these, because the frequency is going to come from this term here and here. So I would typically just pick one. Now, if you have initial conditions and the problem is enforcing those initial conditions, like, then apply them. But again, if all you want is the frequency, you're free to pick one of these, and then you sub into the differential equation. To do that, you need to calculate the second derivative of your function. Sub that second derivative term into this part, sub just the position function into this part, after you've driven the sines and cosines away, and you're looking for the angular frequency. You want to get this function to a point where you've got this guy right here. I always graph it then. I like to look at things graphically, and you look at one cycle. You know that once you go through one cycle, this term has to be equal to 2 pi. That's how you get your period. And then 1 over your period is the frequency. So I hope that this video helps demonstrate how to calculate the frequency of a harmonic system. Have a great day.